going to address what kind of solution that one can think of addressing these challenges. So electricity is a kind of chain. So we all know that we must generate electricity, and from one place to other place the energy has to be transmitted, and then we need to store this energy. So that's where this battery technology plays a vital role in storing this energy. So let's start the main fundamental of these electrochemical energy storage and conversion devices. It's simple oxidation and reduction process. We all know that historically oxidation is a reaction with oxygen, yes, of course, and reduction is removal of oxygen. Okay, so nothing but it's a loss of electrons, oxidation, and gain of electrons. This is actually the school level concept, but still it is the base for all these applications. So this is again, the mnemonic device. Probably we would have all recalled our school days. When we were taught to understand oxidation and reduction, they might have given these kind of tips to remember that. Look at this, Leo Ger. Leo says Ger, that means loss of electron is oxidation and gain of electron is reduction. The other example also oil rig, oxidation and reduction. Okay, these are things to remember. We have been talking these things. Okay, so what kind of revolution that we have seen in the case of energy storage system? Look at these two images, so left and right. So what you see here on the top right is the Belgium car powered by lead acid batteries. Similarly, this is actually nothing but a mobile phone which have been used in the military applications. So the bottom pictures, what you see here, this is a lithium-ion powered Tesla car, and this is the current smartphone that what we are using. See, I'll be surprised to hear if someone says that, sir, I don't have a mobile phone right now. No, actually we will be having one or two mobile phones. More importantly, even that mobile phone also, the charge is not enough. We will be having the backup. There also battery plays an important role. Okay. So these are the things, certainly evidence that we have greatly made the revolution in these technologies. So the other image that I have found for you, actually, look at these 90s. So the audience are watching the live event, what's happening. But after 2010 and even now, we are trying to capture these events. But almost 90% of us, we won't revisit those images or pictures. So due to the curiosity, we are capturing these kind of things. The point that I'm trying to tell you is here, these all things happened. Certainly the science and technology development happened in these kind of batteries. So what are the batteries have been taken dominant in the energy storage technology? So before going to that, we must understand what is energy density and power density that is simply given in the Ragupathy plot. So energy density is the amount of energy that is stored per unit volume or weight. Okay. So then now we understand fuel cells and the chemical batteries are having high energy density. On the other hand, what is power density? Power density is nothing but the amount of energy that you can spend, the stored energy. How quick you can make use of that energy. That is called power density. So supercapacitor are well-known power density devices. So what is actually we need? We need to have both energy density and power density at a higher rate. It's in the it should occupy this region in the Ragupathy plot. So the whole globe is trying to push up the energy density and power density in this direction. So the ideal storage device should possess maximum energy density and power density. So to look at this cartoon, what do you see here? The amount of energy and power. As I mentioned, the amount of energy stored per unit of volume and the power, how fast you can transfer this energy. Look at these two containers being a wider neck, the power, you can quickly make use of that energy. So you can also think of the other scenario where 100-meter running race compare with a marathon. So in the case of marathon, you need to use more amount of energy for a longer period. On the other hand, for 100 meter, you just quick power. So that is your power density. These are the simple example for that. So look at that before going to the advancement in the battery. So a quick recap of the history in the battery technology. So even the Agastya battery, 7,000 years ago, a Sanskrit version written here, but I'm finding difficult to read that. But actually the message is a clean copper plate is put in the earthenware vessel. It is covered first by a copper sulfate and then moist sandwich. After that, put a mercury amalgamated zinc sheet on the top of an energy known by the twin name of Mintra at Varuna. Mintra cathode, Varuna is anode. So water will be splitted into Pranavayu and Udanavayu. That all we know that when water splits into hydrogen and oxygen. So that's where given here. And look at this, the ceramic beaker, the vessel. You know, actually cell is a single unit, and we know Sada. Sada Kuma means like 100 cells connected in the series to get a large more amount of electricity, the chemical energy to electrical energy. So the point is, even 7,000 years ago, our people might have thought about the electricity. So these are the containers that what we have been talking about. Very interestingly, look at this Mitra Varuna, a cathode, anode, and we all know oxygen, Pranavayu, and hydrogen, you know, Udanavayu. These are things. So this is again the components that what I have mentioned in the previous slide, you know, the jar and the copper cylindrical rod, vinegar as electrolyte, and the amalgamated compound as a separator thing. And then later the modernized electricity, the story has started with the galvanic. You know, basically Galvani was a physician. When he was trying to address electricity from the medical field, then he was, trying to, cut this frog. That's the story we know, that animal electricity. Then later Alexander came to know that that is not due to the actual frog, that is due to the component that we use, the copper and zinc, the copper spoon. And then the second part later, Daniel cell, that's what we have been talking about, zinc and copper. And then story went to lead acid battery. Now recently we are talking about lithium ion batteries and lithium air, lithium sulfur, and the modernized organic batteries kind of thing. So now let's talk about the lithium ion batteries. Why lithium ion batteries are so fascinating in the recent years? We all know that due to the amount of energy and the size of the battery. Look at this Ragon plot again, comes here, the energy density. So what you look at here, energy density of various storage batteries, starting from lead acid battery to lithium ion. This is nickel cadmium, nickel metal hydride. If you look at the energy density of lithium ion is 3 times higher than that of lead acid battery. Lead acid battery is just 50, lithium ion batteries it's 150 and above. That means one lithium ion cell can replace 3 numbers of lead acid batteries or even nickel cadmium batteries. So that's the reason why these lithium ion batteries plays a very predominant role in the energy storage technology. So how do we calculate the energy density? So the energy density is being calculated with this formula, current and volt. We all know that is watt here, and of course the time, watt hour per kg. Kg is the weight. So why lithium is so special here? If you look at the standard reduction potential in the electromotive force series, so lithium plays very high redox potential, minus 3.05. So since voltage is upper, then the energy density will be a higher rate. Another important point that we all know that metallic lithium, being a soft metal, it has very, very less atomic weight. So since the weight is in the denominator, you will be getting again high energy density. So these are the 2 important factors made this lithium ion is so fascinating in this field. So this is electrochemical cell reactions for a simple lithium ion batteries, what you see here. More importantly, I must tell you the fact that here, when you look at the energy, that is electrochemical energy in terms of thermodynamics. So this is, we all know that nothing but relation between thermodynamics and electrochemistry. Delta G is equal to minus N of E. So when delta G is negative, then the reaction is spontaneous. And we know that if it is positive, there is no reaction. And if it is zero, we all know that it's in the equilibrium state. Okay, in electrochemistry, there are two things. So the electrochemistry title says the influence of electricity for the chemical reaction. It's simple. So chemical reactions produce electricity, or electricity causes some kind of chemical reaction. So that is your water electrolysis. So look at these lithium ion batteries. What do you see here? Cathode and anode. In this case, anode is metallic lithium or lithiated carbon. So, and what do you see here? The lithium ions are shuttling from cathode to anode and anode to cathode. So knowingly or unknowingly, every one of us will be carrying the lithium ions in our pocket, right? So that's what the chemistry works here. Look at this, when lithium comes from cathode to anode, the corresponding discharge, you will see that. And charging is the reverse. Charging means, see here, and discharging means you are talking through your phone. So the simple reaction involves oxidation reduction, the same concept what we have seen. So this is the variation in the potential. Okay, so what about the history? So here is a gentleman called Rudy from the University of British Columbia, who was the first guy who has proposed this lithium technology. I'm sorry, this is not lithium ion, this is lithium battery. Since because he used anode as a metallic lithium. Okay, so he has constructed a cell, lithium cell, using a metal sulfide and metallic lithium, and he could get the voltage 2 point something. That is due to the metal sulfide. If it is metal oxide, then obviously it is 3.5 and above. Okay, so what was the problem in that lithium cell? If you look at this, when they used metallic lithium, and they found that dendrite growth on the anodic side. So what does it mean? See, this is the fresh shell after assembling metal sulfide and lithium. Or repeated cycling, you could see that there is a kind of formation of needle kind of thing. So that causes an uneven growth of the lithium ions on the metallic lithium. So what happens? This dendrite growth will puncture your the separator, which is placed in between the anode and cathode to prevent the short circuit. So this was the initial battery. What happens actually? This Moly cell, there was a famous company, the lithium battery used in the Kodak camera. So most of us, now we recall. You remember before this smartphone, we used to have the Kodak camera. There 36 or 32 pictures only could be taken. So now imagine, even in your smartphone, you will be storing like 10,000s of images. So that is the real revolution happen in this kind of technology development. Okay, so then people thought about how to replace this dendrite growth electrode. Then people went for a lithiated carbon, that is called lithium plus. So metallic, there is no charge, it's Li. So then they thought, okay, we should have the lithium property, but at the same time we don't want to have this issue, dendrite growth. Then people went for metallic lithiated carbon, so where they have lithium plus. So that's where it is being called lithium ion batteries. So now you think about lithium battery, they use only metallic lithium. The other one, lithium ion, where they use directly lithium ions in the intercalated carbon. So the story started lithium ion, lithium polymer, then lithium air, lithium sulfur, and so on. Okay, so these are the various anode and cathode material tabulated here. Look at these all cathode material, the higher potential, and these are anode material. So when you want to combine these two anode and cathode material, you have to be very careful in fine tuning these in order to have a wider potential window, because that potential will determine your energy density. Okay, small scale to large scale, the development. So the story started with lithium cobalt oxide. During 90s, Professor John Goodenough, so who is the last year Nobel Prize winner for this lithium ion technology. He was one among three. So Stanley Whittingham and Akira. So these three were awarded Nobel Prize for their, the development of these lithium ion batteries. So this material was discovered by John Goodenough when he was working with kind of oxides.